Okay guys, welcome back. Today we're going to finish up the Introduction to Physics guided notes. So please have your workbooks out and be filling in all the information as we go through these video slides. Also, one more thing I'd like you to have out today is a scientific calculator. We're going to use it a lot as we go through these slides. So please have access to a scientific calculator. If you don't right now, please hit pause and get one before you continue. Okay, so let's start. This whole lesson is mostly about scientific notation. And hopefully you have a little bit of background with scientific notation. If not, that's okay. Because we're going to go through all the basics of it in this video. So here's the deal. In science, we deal with some very large numbers. Really large numbers. For example, 1 mole of a substance, as you learned in chemistry, is Avogadro's number of atoms. So look how large this number is. If you wanted to put this number in a calculator, a regular calculator, it just wouldn't work. So that's why we've got to learn scientific notation. Also, though, in science, we deal with some very small numbers. For example, the mass of 1 electron is this number. Look at all of those zeros before the 9(1) kgs. I mean, the mass of an electron is very, very small. We don't really want to write out all of those zeros either. So that's where scientific notation comes into play. It makes it so much easier to deal with really large or really small numbers. Imagine the difficulty of trying to calculate the mass of 1 mole of electrons. So 1 electron has this mass. If we wanted to calculate the mass of 1 mole, we'd times it by the number of electrons that there are in 1 mole, which is this bottom number, and then times these two things together. If you had to do this, just longhand, trying to keep track of all the placeholders would just be a nightmare. And so that is why we use scientific notation. So, what is scientific notation? Here's the definition. It is a method of representing very large or very small numbers in this form. So this is the general form for scientific notation. The m in this example here, the m is called the coefficient. So this number out front is called the coefficient, and it's a number between 1 and 10. So it falls in between 1 and 10, that coefficient will. Okay, so we've got m, the coefficient, times 10 to this n. The n is called the exponent. And it's either a positive or a negative number, so it can be negative as well as positive. All right, so let's deal with this a little bit. Let's work with this. The largest diamond in the whole world is called the Hope Diamond. At least it was at one point. I think there might be one bigger now. Anyway, the Hope Diamond, the number of carbon atoms in the Hope Diamond is 4.6 times 10 to the 23rd. So if you were to write that out in standard form, 4.6, then you would have to add 23 zeros to the end of that. So 23 times, we'd have to move this decimal 23 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. And that decimal would be right there. Huge number in standard form. But in scientific notation, it's much more manageable. So, standard form, I've been saying this a little bit. Here's what standard form means. It is when the number is written all the way out. For example, 600,000. That's written in standard form. Scientific notation, though, is when a number is written in the form of m times 10 to the n. An example of 600,000 written in scientific notation is 6.0 times 10 to the fifth. So we're now going to learn how to go from standard form to scientific notation and vice versa. You've got to be able to learn how to take a number in standard form into scientific notation and also go back from scientific notation into standard form. After this lesson, I hope you will think that it's pretty easy. Okay, so here's a number. Let's see, that would be 2,500,000,000. It's a very large number. So if we wanted to put this number in scientific notation, there's a few steps. Step number 1 is to insert an understood decimal point. There's an understood decimal point right here. Okay, so we insert that understood decimal. Step 2, decide where the decimal must go so that one number is to its left. Always in scientific notation, we want it to go where there is only one number to its left. And if we put it right here, there would only be this number 2 to its left. So that's one number to its left. Okay. Step 3 is to count how many places you bounce the decimal point. So we're going to have to bounce it all the way to here. So let's count how many times that is. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 9 times we had to bounce the decimal point. Step 4 is to rewrite it in the form of m times 10 to the n. The m is the coefficient. That's going to be this number, 2.5, times 10. The n is the number of times you bounced the decimal. We bounced it 9 times. And so that is going to be how it's written in scientific notation. Okay, so I guess I got an animation. We put in the understood decimal point. Step 2, decide where the decimal must end up so that there is one number to its left. So it's got to be going all the way over to there. And step 3 is to bounce the decimal until you get there. So we count how many times we got to move it, 9 times. And that becomes our exponent. And there's our answer. The exponent is the number of places we move the decimal. So this number 9 is how many times you bounce the decimal. All right, now here's another example, except for this is a very small number. So we don't need step 1. We already have a decimal here. It's not understood. It's there. That's where it's at. So we're going to go ahead to go to step 2. Decide where the decimal must end up so that there's one number to its left. Well, if it's going to have one number to its left, that decimal's got to end up right here. Step 3, count how many places you bounce the decimal point. So we're going to go 1, 2, 3, 4, and 5 times. So make a note of that. We moved it 5 times. Step 4 is to rewrite this in the form of m times 10 to the n. My m, the coefficient, is going to be 5.79 times 10, and the n is the exponent, and that's the number of times you bounced the decimal, which was 5. Okay, now there's a wrinkle with this one. This one's a little different. If you bounce the decimal to the right, that means you're going to have a negative exponent. So I need to put a negative sign in right there, and there's my answer. Okay. So let me just say this up front. If this, in standard form, the number is less than 1, so it's a very small number. If it's less than 1, you're going to have a negative exponent when you write it in scientific notation. If the number is big, it's way larger than 1, then it's going to be positive. Smaller numbers less than 1 will have a negative exponent. Okay, so let's go through this. You put the understood decimal here so that there's one number to its left. You count the number of times you got to bounce it to get there, which was 5. Because it went to the right, that exponent is a negative 5. Okay, so if the standard form number is 10 or larger, the exponent will be positive. So if it's larger than 10, your exponent is going to be positive. However, if the standard form number is less than 1, so let's say it's less than 1, it's a very small number, your exponent is going to be negative. Let me show you a couple examples here. 800. This is large 10 or larger, so my exponent should be positive when we write it in scientific notation. It's 8 times 10 to the second, so that's why this is positive. However, this number here is very small. It's less than 1. And you'll notice when you bounce the decimal, you're going to have to go to the right. So your exponent is going to be negative. So it's 3.43 times 10 to the minus 5. So hopefully you kind of get that and you remember that because you're going to see that a lot. So what I've got now is a bunch of practice problems to go through. So let's start with practice problem number 10. It says the diameter of the sun is 1,392,000 kilometers. Write the diameter of the sun in scientific notation. So this number is our standard form. It wants it in scientific notation. So let's go through those steps. Step number 1, insert an understood decimal place. My understood decimal point is right here. That's where it's understood to be. Step 2 is to decide where the decimal needs to go so that there's one number to its left. It needs to go right there. The next step, we've got to count how many times we need to bounce the decimal. So 1, 2, 3, 4, 5, 6. So I bounced the decimal 6 times. I'm just going to make a little note of that. Now, last step is to write it in this form, m times 10 to the n. My m, the coefficient, is the number. So it's going to be, in this case, 1.392. You keep all the non-zero numbers in your exponent. Times, my exponent is going to be the number of times I moved the decimal, which was 6. And this number is definitely a large number. It's way larger than 10. We bounce it to the left, that's going to be positive. So there's my answer. And we got it right, so very good. So I hope that you're getting the hang of this. Let's go to practice problem number 11. It says the density of the sun's lower atmosphere is 0.00000028 grams per centimeter cubed. Write this number in scientific notation. So, again, this is a very small number. It already has a decimal place. It shows us where it's at. We just need to decide where it needs to go so that there's one number to its left. That decimal's got to end up right here so that there's one number, the 2, is to its left. Now let's count how many times you got to bounce the decimal. 1, 2, 3, 4, 5, 6, 7, 8. We bounced it 8 times. Now let's write it in scientific form. So it's going to be 2.8 times 10. We bounced it 8 times. However, we bounced it to the right. This number is less than 1, so that's going to be a negative 8. And there's my answer. Okay, we got it right, so very good. Let's see if you guys got the hang of this. So practice problem number 12. I want you guys to try this one on your own. So if you're watching the video, please hit pause. Try it. Once you have your answer, hit play and see if you got it right. Okay, so let's see how you did. Hopefully, you inserted an understood decimal place right here. We want it to go so that there's one number to its left. We need it to go right here. So we're going to bounce it 2 times. 7.0 times 10. We bounced it 2 times, so the exponent is going to be a 2. It's larger than 10, so it's going to be positive. We bounced it to the left. And there's my answer. Okay, so hopefully you got that right. Now, do you need this 0.0? Not necessarily. You could have just put 7 times 10 to the second. It would be the same thing. Practice problem 13. Express the following number in scientific notation, 38,000. So again, please try this one on your own. Once you have an answer, then hit play again and see if you got the answer right. Okay, let's see how you did with this one. Hopefully you put an understood decimal place in right here. We want it to go right here so that there's one number to its left. 1, 2, 3, 4 times we bounced it. So let's write it. 3.8 times 10 to the 4th. It's a large number. We're bouncing it to the left, so that exponent is going to be positive. And there's my answer. And we got it right. Good job. Okay, practice problem 14. Let's have you guys try this one. So please hit pause right now. Try it. Once you get your answer, hit play and see if you got it right. Okay, let's see how you did with this one. We already have a decimal place here, so let's just decide where it needs to go so that there's one number to its left. It better go right here. So let's count how many times we have to bounce it. 1, 2, 3 times. So this is going to be 5.4 times 10 to the 3rd. But be careful, we're bouncing it to the right. This number is less than 1. It's got to have a negative exponent. So 5.4 times 10 to the minus 3. All right, let's try practice problem 15. Express this number in scientific notation. Okay, again, please hit pause. Once you have your answer, hit play, see if you got it right. Okay, let's see how you guys did. Hopefully you put an understood decimal point in right there. We want it to go so that there's one number to its left. We're going to have to go right here. So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we bounce that decimal 11 times. So now let's write it in scientific form. 6.85 times 10 to the 11th. This is a large number. This exponent, we bounce the decimal to the left, so it's going to be positive exponent. So there's my answer. And we got it right, so very good. Okay, last practice problem for this section. It says express the following number in scientific notation. Again, let's see if you can do this one on your own. Please hit pause right now. Try it. Once you have an answer, then hit play and see if you got it right. Okay, let's see how you guys did. We have a decimal already. We want the decimal to go so that there's one number to its left. So 1, 2, 3, 4, 5, 6, 7, 8 times we bounce the decimal. So in scientific form, that's going to be 7.6 times 10 to the 8th. But this number is very small. It's less than 1. We had to bounce the decimal to the right. That means it's going to be a negative exponent. So 7.6 times 10 to the minus 8 is our answer. Okay, let's switch gears for a second. This is where you're going to need your scientific calculator. So if you don't have one, please get one before you continue this part. And we're going to use scientific numbers with it. So let me teach you how to enter a scientific number into your calculator. So everyone needs to have a scientific calculator. Here's the first problem that I would like to go over. Okay, so we have this problem. It says 2.32 times 10 to the 4th times 7.47 times 10 to the minus 2. Now we've got to learn how to put scientific numbers into our calculator. And for a lot of students this gets really confusing and they make a lot of errors. And all of their calculations will be incorrect. So please pay attention to this point, to this part, and I'll show you how to do that. So before I start, here's our calculator that we have in this class. Yours at home, if you have a different one, might look a little different. But they're all pretty much the same. Your buttons might be in different locations, but they're all pretty much the same. So I wanted to bring your attention to a couple of buttons before we start. Okay, first of all, I call it the big E button. So the big E button, let me show you where that's at. So if you look on this calculator right here, you'll see this E, this capital E, capital E. And it's right here on our calculators. But to get there, there's not a button for it, unless you hit the second function first. So you're going to have to hit this button, and then x to the minus 1, and that will give you this big E button. I'm always going to say the big E button, so you got to know where to hit that. So second function first, then hit x to the minus 1, and it puts that function in there for you. Why I like to use the big E button? It's a shortcut. The big E is a shortcut for times 10 to the something. So, and it helps us keep everything in order, and our orders of operations are correct if we use it. So, here's how I would put this in my calculator. I would put 2.32 times 10 to the fourth. Now, this times 10 is abbreviated with the big E button. So hit second function, then hit this x to the minus 1. It will put in a big E for you. Again, that means times 10 to the something. So we don't have to write this in our calculator, but we do have to tell it the exponent. It's a 4. And so when you're putting it in your calculator, 2.32, second function, x to the minus 1 will give you the E, and then just hit 4. So that's what this means. Then you're going to hit times 7.47. Again, the times 10 something is abbreviated with E. So second function, hit this button, x to the minus 1. Now, we have a negative exponent. How do we put in a negative sign? Well, students will sometimes make the mistake of hitting the minus button. In fact, this is a negative 2, so we're going to hit this button down here. This is the negative button. So hit that button, it throws in a negative sign, and then hit 2, and you've got it. Okay? And then all you have to do is hit equals. So I'd like you to try that right now and see if you can get the right answer. So 2.32, second function, go to that big E button, 4 times 7.47, big E button, to the minus, or to the negative 2. And you should get this answer, 1,733.04. Okay. So if you've got that answer, great, you're doing it right. If you didn't get this answer, you're hitting something wrong, and I can help you in class or just rewatch this portion of the video. Now I also wanted to show you another function your calculator can do. If you wanted to express this number in scientific notation in your calculator, how would you do that? Okay, well let me show you. You see right here where it says SCI. That means scientific. That's going to put it in scientific form. But again, there's not a button for it. It's above the button, so you've got to hit second function, then this DRG button, and that will give you the SCI. So let's try that now. So hit second function, DRG, and then it's going to look like this. It's going to have FLO, SCI, and ENG. So you're going to have to scroll over using this arrow to this SCI function and hit enter. Hit the equals button. And that will put it in scientific notation. Now, if you want to go back to standard form, how would you do that? Well, hit second function, DRG button, and then slide it back, hit this left arrow and go back to flow. And then hit the equal sign. And that puts it back into standard form. So I hope that you are becoming familiar with how to go from standard form to scientific notation and vice versa. Okay, now I've got a couple of practice problems to see if you've got it down. So practice problem number 17. It says, find the answer to the following problem using your calculator. So I want you to put these numbers into your calculator and see if you can get the right answer. So please try this on your own first. So hit pause right now. Do it on your own. Once you have your answer, then hit play again and see if you got it right. Okay, so let's see how you did. Hopefully you put in this in your calculator. 3.45 times 10 to the something, we can abbreviate with the big E button, to the negative 5. Adding it, so hit the plus button, 8.76, again we can abbreviate that with the big E, and we've got the negative 4. So if you do that, and then hit equals, hopefully you got this in standard form, or if you wanted to express it in scientific notation, you could write it this way. Either one, they're exactly the same number. Either one works. If you got that number, great, you're doing it right. If you didn't, please try and figure out what you were hitting wrong so that you can fix it. We've got to figure this out because we're going to be using this all year. Okay, let's go to practice problem 18. This is my last one, my last practice problem for this video. So it says, find the answer to the following problem using your calculator. This time, we're going to divide two numbers in scientific notation. So, please try it on your own. Hit pause right now. Try it on your own. Once you have an answer, hit play and see if you got it right. Okay, so hopefully you have an answer by now, and you put this in your calculator. 5.43 big E to the 5th, and then you hit the divide button, and then put 9.32 big E to the negative 4. If you did that correctly, you should have got this answer. 5.83 times 10 to the 8th. Hopefully that worked out for you. All right, now we're going to switch gears a little bit and talk about a couple of new topics. First thing that I want to talk about is the difference between these two words, accuracy and precision. So let's go over their definitions. Accuracy refers to how close a measured value is to the accepted value. So basically, accuracy is how correct you are, how close you are to the accepted value. Let's contrast that to what precision's definition is. Precision refers to how close a series of measurements are to one another. So when you talk about precision, we're talking about how consistent you are. And so I've got an analogy at the bottom to help us kind of understand the difference between accuracy and precision. So this is a bow and arrow example. You shoot the bow and arrow at this target. Let's say you load an arrow and you hit the bullseye with your one arrow. Well, you were very accurate. You were right on the accepted value, or right in the bullseye where you should have been. But it says nothing with precision. It says it has nothing to do with precision because you only shot one arrow. Remember, precision refers to how close a series of measurements are to one another. So you would have to shoot more than one arrow to see if you were precise. Okay, let's go to the second example. Let's say you loaded 3 arrows, you shot, and you hit boom, boom, boom. Didn't hit the bullseye, but your grouping was really close together. So this is an example of something that is precise, but not accurate. They're precise because the grouping is really close together. But you're not accurate because you didn't have the accepted value, you didn't hit the bullseye. Okay? This is the one we strive for in science, is accuracy and precision. So you load 3 arrows, your grouping is really close together, and it's on the bullseye. That is accurate and precise. And then finally, this is what we hope never happens with science and taking measurements, but sometimes it could. You shoot 3 arrows, the grouping is really far apart, and it's not even close to the bullseye. So you are not accurate, nor are you precise. So in physics, we're going to be doing a lot of measurements. What could cause us to be precise but not accurate? Well, if you're using instruments that aren't calibrated correctly, your grouping is really close together, so all the values are close together, but they're not correct because maybe it's not calibrated right. Maybe there's an error with your instrument. Or maybe your measurements, how you're calculating the measurement is off. Something's off, but I would look to the instruments or your methods of measurements there. We always strive to be accurate and precise. Okay, let's go to graphs and we'll finish up this lesson with graphs. So a graph is a visual display of data that makes trends easier to see than in a table. So a graph is a visual display. Here's what I'm talking about. This is sources of chlorine in the stratosphere. Now you can look at a table and get all of the information that a graph would give you. But this data table is not very visual. So over here is our graph. We have a pie graph here. Notice, just looking at it, visually, you can already get a lot of information just by looking at it, a lot faster than you can just from the table. And so that's why graphs are used a lot in science writing and in publications. They take what's in the data table and they make it visual. A circle graph or a pie chart has wedges that visually represent percentages of a fixed whole. For example, this was a pie chart or a circle graph. This whole circle represents 100%, but it's divided up so that visually you can see how each one stacks up. You can also have bar graphs. They're often used to show how a quantity varies across different categories. Always important when you're looking at graphs, read what the axes are telling you. So this is magnesium content in milligrams on the y-axis. The x-axis is food serving, so different categories. We've got halibut and different categories across the bottom. On a line graph, the independent variables are plotted on the x-axis. So the independent variable is on the x-axis. Your dependent variable is always going to be on the y-axis. That's very important. And let me show you what I mean. I'm going to use this temperature versus elevation graph to explain it. So if you're going to go at different elevations, notice the temperature is dependent on the elevation that you're at. So temperature is our dependent variable. It depends on the elevation. So you always put the variable that is dependent on the y-axis. And you'll notice here the trend is as you move to higher elevation, the temperature goes down. So if a line through the points is straight, the relationship is linear. So if you plotted 2 points, and that's a straight line through both points, that's a linear relationship. And this can be analyzed further by examining the slope of the line. Hopefully you remember what slope is from your math class. Slope is the rise divided by the run. So you take the rise over the run. The rise is going to be your y-axis, so it's the change in y. And the run is going to go on the x-axis, so it's your change in x. We'll spend some time learning about slope later. But that's just, hopefully that kind of jogs your memory from math class. And then finally, interpreting graphs. So, interpolation is reading and estimating values falling between 2 points on a graph. So if we had 2 points on this graph, this blue line right here that I'm drawing on, if we wanted to examine and analyze points in between those two measurements. This would be called interpolation. But sometimes we want to look outside of our measurements and project what it's going to be in the future, or maybe the past, what it was in the past. This is kind of like a projection. So this is called extrapolation. It's estimating values outside the points by extending the line beyond the graph. Now we can kind of get a general trend here from the data points. This is the line of best fit. We could estimate at 60, I don't know, maybe it's going to be about right here, around 120. Okay? We could also estimate at 0, maybe it's around 20. That's called extrapolation, is when you're estimating values that fall outside of your graph. Okay, so did you learn how to write very large numbers or very small numbers in scientific notation? I hope that you learned how to do that and put it in scientific notation. Did you learn how to take a number from standard form to scientific notation and vice versa? So can you go from standard form to scientific notation and then vice versa? Number 3, how to enter scientific numbers into a scientific calculator. Did you learn how to use the big E button? I hope so. Number 4, did you learn the difference between accuracy and precision? And number 5, did you learn about graphs and how they work and some of the different terms that we'll use in describing graphs? And I hope that you did. Alright guys, that's it for this lesson. Before I stop the video though, you now know enough to do the scientific notation worksheet in the student workbook. So please go there. Again, it's called the Scientific Notation Worksheet, and let's get that done.